introduction. Yeah, and he will tell us about modeling and verifying mathematics by computer.
Thanks, Art. And just so y'all know, I am recording this part of why I want to talk in here because I people ask me this kind of stuff, and I thought it'd be nice to have a recording of this to put on my YouTube channel. So, but you're not on camera, only I'm on camera right now. So just don't come in this corner, and nobody will see you. If you are interested, if I accidentally say anything interesting today, clots.org is my website. The top blog post has links to various things, including the slides, which are right here. I got a slideshow that has a few notes I'm going to have on it, and I'm going to make sure that this works. If I draw in like white right here, wait, why aren't you working? Come on. I want you to let me change the color. Strange. Pencil first, then, here we go. All right, now if I draw a smiley face, people can see that. If I get the eraser, people can erase that. So I'm going to talk about formal verification of mathematics, but I always like to, the whole theme of my sabbatical last spring was this very broad idea of what is the socio-technical infrastructure of mathematics research. So we all, have this intuition, those of us who are math researchers, we know what we think of as math research, but I spent some time thinking last spring and working on a few different software products, which are really driving mathematical collaborations and advances today. So what if I were to ask you, what is math research, or what are products of math research or math research activities? What kinds of things do you think of? Papers. Papers, okay. So we can start with drawing. You got papers, okay. So we got papers, great. So hopefully maybe there's an X squared in there because it's math paper, great. So if I just write, like I get a piece of notebook paper that says dead markers, and I write a squared plus b squared equals c squared, that's a paper, that's a math paper, but that's probably not the kind of paper you were thinking about, right? What kinds of math papers are you thinking about?
Original, groundbreaking.
Groundbreaking. So we have different mathematicians writing different papers. All right, and then these are original, because now it's original mathematics, right? That's not just the Pythagorean theorem all over again. But then I don't just write a piece of, I just don't write my math on paper and then slide it underneath my desk and I'm done, right? What I gotta do with it? Type it up. So maybe I type it up. So now it's in LaTeX. Great. And I have to publish it, which means that I have to take these tech files and then I do what with them? I guess I submit them to, I don't know, some journal. And then they post it immediately. No, they don't. They don't post it immediately. What does the journal do with those? Peer review. Yeah, they send them out to other people to read. Or really, you're sending it to the journal. You're probably sending it to an editor that's at that journal. Yeah. And then that editor picks the people who is an expert in this field that can give me feedback, because the editor doesn't have time to read all these papers and verify all these papers or deem them worthy of the exclusivity of that particular journal, because it's not always just correctness that we care about. But we get the feedback, on the accuracy of the math or the quality or importance of the math, and they send that back to the journal. They send it to the editor. And then if the editor so deems it worthy, with the input of the referees or reviewers, whatever you call them, then it goes to a website. Okay. There we go. We're on the World Wide Web. Hooray. And we used to do this a lot more, but maybe we even went to a printer. And then you went to a library, like an in-person library. Okay, but maybe less of that's happening now. Maybe that's more the library has the digital subscription. Okay. That's not all the activity that happens in mathematics, though. It's probably a big thing. I mean, certainly what counts, though, these papers that get put on the website, that's what counts for a lot of us as our big artifact of research, but we also do other things.
Talks.
Give talks, like I'm giving a talk right now. So maybe separately, I'll be at a blackboard and I'll give a talk, or someone else will give a talk about their mathematics. And they'll do that at, their university. They might do it at a meeting, conference. Okay. And those things don't just happen though, right? Yeah. So there's a whole bunch of logistics. I mean, here at the seminar, not too much done. Art does a great job keeping us all organized. I just emailed him, say, hey, can I talk? And he was like, yeah, you're not a complete kook. I guess I can let you talk up here. But if you're going to a bigger meeting or a conference, then there's a lot more logistics that are involved there. I mean, not to mention the logistics of the web and the journal, right? You can't just build a website and just plop files up on the website. You've got to have, well, if you're at the journal I'm an editor at, you do just email files around, which is terrible. I'm trying to help them work with that. But maybe there's an actual journal, article submission system and a reviewer assignments, and there's all these issues of like whether we want to have double anonymous reviews or maybe double public reviews, depending on what's going on there. And so the point of this is that it's all just a big complete mess, and it's kind of something we've just stuck together over the years. And it's something that I've been thinking more and more about in terms of how can we make these things, these processes as efficient as possible. And the thing I want to talk about today is this kind of what makes mathematics correct and official, right? That's kind of the job of the journal at some stage, right? In our field, at least, there are adjudicated, like refereed meetings, and being in the proceedings of a conference, if you're a computer scientist, is a much bigger deal than in mathematics, right? Because they don't have time for journals. Things are moving so fast for them that it's really being able to present at the conferences that is their big artifact, and that makes it really difficult for them to get tenure in some places where they don't understand that distinction. But for us, journals are still seemingly the big, you get your math into a peer-reviewed journal, then you have done something, you have created new mathematics, and it's absolutely 100% correct every time, right? No mistakes. And all the active researchers are chuckling because we've all read papers with errata, minor or larger, depending, in the literature. I remember, not to name names, I am recording this, but I did read a paper in the proceedings of the AMS about an area I'm quite interested in. Yeah, it was wrong. It is still wrong well, let me rephrase. The result might be correct, but that proof was not sufficient, right? They used a completely wrong characterization of a particular topological property. And I emailed the authors, and they were, because I was trying to understand this paper, so I was emailing back and forth with the authors. And when me and my co-author, who I was working through this with, because we thought we had some extension of it, we pointed out the mistake. They stopped emailing us, so, which is kind of a shame because I used to respect this person. Anyway, but it's frustrating. It was, again, I'm not certain the result was wrong, the theorem was wrong, but it definitely was not proven in the paper. It was not sufficiently supported because of a subtlety. Because let me rephrase: it is true for all strongly paracompact metrizable spaces, but not all metrizable spaces are strongly paracompact. In the examples of metrizable but not strongly paracompact spaces are really, I could never work through it. It's such a subtlety that we never come up with a counterexample because those examples are just really hard to work with. And then, so we did write a paper and submit it to the proceedings of the AMS, pointing out the error and giving some results. And they said, this is too technical for us, go submit it somewhere else. I'm like, okay, so you published something that's not, we show why it's not supported, but now we're gonna go, because it got too technical, it was. But the only reason the other paper got accepted was because they hand waved too much and they said something that was not true. Fun times. Okay. All this to say, my soapbox is, how can we reduce this risk of incorrect mathematics? One. And two, how can we use computers to make mathematics more interactive, especially when we're working on our own, when we don't have the rubber duck or a colleague to talk about the mathematics too? How can we get this stuff checked quickly and with a high degree of confidence? And that's where I think formalization of mathematics, formal proof verification, could be really important and come into play here. So, that's my claim. Formalization is the future of mathematical proof, but don't take my word for it. There's a few papers that have come out recently. First one I'll point out is Kevin Buzzard. He's at the Department of Mathematics at the Imperial College London. He recently got a £1 million grant to formalize a proof of Fermat's theorem. Now, this is something that was conjectured long ago, and the first generally accepted proof, I believe, it came in the mid-1990s. And it's a very simple, if you're not familiar with it, it's a very simple claim that the only way that a to the n plus b to the n can equal c to the n, where a, b, c are integers, Well, n has got to be 1 or 2. 1, it's easy. 1 plus 1 to the 1 is equal to 2 to the 1. Okay, easy. And of course, 3 squared plus 4 squared equals 5 squared. Pick your favorite Pythagorean triple. Easy. The fact that you can't do it for cubes or fourth powers or fifth powers, very subtle. I'm not a number theorist by any stretch of the imagination. I don't really know exactly how that is done. But it was proven in the 1990s. But now Kevin's got a grant to basically spend the next 5 years trying to, and I think he said in his blog post announcing this, is that I don't know if I'm actually going to get it done in 5 years, but at least we'll take a big chunk out of it. And it's not just him working on it. There's a whole community, and I'll talk about the MathLib community here in a bit. But he wrote in his paper, it was on the archive, I think in December 2020 is when I noticed it in the archive, and then got accepted into the ICM proceedings in 2022. What is the point of computers? A question for pure mathematicians. And I think it's a paper that's worth, a read for anyone who's interested in kind of how mathematics might be changing in the next decade. One thing that's kind of huge in the past, few years, I guess, for some value of few, is that we are no longer just like crunching through big search spaces, like 4-color theorem, trying to just brute force every single possibility, and there you go. We had a computer check a million different possibilities, and they all worked out the way we thought they would. So therefore, this theorem is true. But we can't do stuff about, we can't prove there are infinitely many primes by just crunching through all the prime numbers, right? That will not work. But with proof assistance, these programming languages that basically model the axioms, your favorite foundations of mathematics, CFC, category theory, type theory, whatever, these computer proof assistants understand the rules that humans do mathematics with. And they are able to then to let you express the mathematics that you would normally run on paper. You can express it in a very technical sort of way as code. And they can verify whether you said something that's correct. And they can even have some semblance of reasoning. I have to shout, the reason this paper came across me is I was really tickled because they got a shout out for the pi base here, because I think that another kind of important aspect of this, and this is something that I think is going to be, I'm not talking about so much about it today, but I think it's kind of important, is that we can, even if you sit here and you see me do this formal mathematics here in a moment, and you think that this is way too technical, way too much work to prove really simple. I'm going to prove really simple mathematics for you today in formalized language. But I believe there's a middle ground here. I think semantic search and mathematical databases, which I've talked about before this colloquium, have this thing called the pi base, which is something a buddy of mine from grad school created when he was a master's student, and he and I have kind of worked on it together. And so it's a catalog of, and I'm thinking about, all right, you were talking about your atlas, right, for knot theory. This is the atlas for general topology right here. It was based upon a book that had like the first 100 or so spaces, and now we have, twice as many spaces, but where it's really exploded are all the different theorems, or properties and theorems connecting these properties together. And it does some automated deduction. So things like, if I want to know what all the compact Hausdorff spaces are that aren't normal, it'll yell at me because that's impossible. Every compact Hausdorff space is normal. But if I want it to be not first countable, then it gives me looks like 8 different examples of that. And so this is a kind of like really baby's first formalization. This is what I've been working with this for almost a decade, I guess, at this point in some capacity with this product. But I've never gone full-fledged into formalized mathematics because it just seemed like it was going to be hard. I'm not going to lie. And I had enough to do, and I needed to get tenure. And I kind of regret waiting so long. So I'm going to show you that hopefully I'm going to convince you that's not so scary by the end of today. But I think there's lots of databases out there too. If you're interested in just like how do we just formally model results, but not necessarily the proofs of those results, then that's something I'd be happy to talk about later as well. Terry Tao, probably heard of him, Fields Medalist, MacArthur Fellow, pretty sharp fellow, considered one of the greatest mathematicians of our time. He gave a colloquium lecture at the last JML called Machine Assisted Proof. And I think if you follow him on socials, he's on the Mastodon these days. And if you follow him, he's talked a lot about not just formal proof of systems, And not just like the more classical machine learning algorithms and these other sorts of methods for doing doing mathematics or helping assist with mathematics, but he's really into the AI stuff, like the generative AI, which I'm kind of skeptical about in some sense, but he's really into it. And, you know, it's something that you could read his paper to kind of explain where he thinks AI is going to go. But one thing I like to point that I think is important is that while he's very bullish on the future of formalization as being a tool to get better mathematics, to get more efficiently done mathematics, more collaborative mathematics, it's too clunky right now. You're going to see me do some coding in Lean in a moment, and you're going to go like, this is a lot of work for just a really simple result, and it's true. That's just because we don't have the tools yet to help take our intuition and turn them into the code. Although I will show you a few cases where I am able to do that, using a little bit of, not generative AI, but it is AI. And a particular formalization language that I've gone into is Lean. Now, this is not by far, it's actually one of the newer formalized proof assistants out there. I remember in grad school piddling around with Mazur, I believe was the name of it. I never really got into it. It was too hard to install. And that's another thing that, you know, last semester in my sabbatical, I've thought a lot about, like, you know, there's so many tools that can help us do better mathematics, but they're so hard, like it's just so tedious to install on our computers and get up and running. But there's some cool web technologies these days that make it much easier to get into these different types of projects. But in any case, Lean, I'm going to show you how to just use a web browser to do Lean today. And why would you use Lean? Well, again, one reason, if you, besides just, you know, well, the one I've kind of talked about is syntax errors when you make a mistake, right? You can't screw up. You can't screw up your proof, because if you screw up your proof, it'll raise an error. It's not like when I write proofs on paper and then I sit down to tech them up and I go, crap, that was wrong. Or worse, I have to give them to a colleague and they go, I don't understand this. Okay, why is this true? And I go, oh, it's not true. This is why. It won't let you get away with nothing, right? It will tell you when you've made a mistake. And it does so in this interactive method that I'm going to show you here in a little bit. So you know instantly. And once you get used to the workflow of writing your proofs in a formalized environment, it's actually pretty fun. It's like a video game, right? You're doing mathematics, but you're also kind of like trying to turn the red X into the green check mark. And I actually think it's kind of neat once you get into the flow. So if you decide you want to get started with formalized mathematics, I did this like a year before I really started actually doing formalized mathematics. There's this thing called the Lean game server and the thing called the natural number game. And we're going to play a few levels of this. I told you that formalized mathematics is kind of like a video game. Well, this is taking this to the extreme, right? So here we've got, you know, grassland, desert land, pipeland, you know, shout out to all my Super Mario Brothers fans out there. But it's actually tutorial world. So this is just teaching you the basics of formalized mathematics and Lean. And so here's an example of what I like about this is it pairs mathematical statements, something that we as humans, you know, that we are mathematicians would read. If X and Q are arbitrary real numbers, then 37X plus Q should equal 37X plus Q. I hope so, right? All right. This is how this would be formalized in Lean. You've got some objects. You've got that X and Q are arbitrary natural numbers. And our goal, the if then, so the if is the objects, the then is our goal. Our goal is to prove that 37 times X plus Q equals 37 times X plus Q. And golly, I hope that's an easy thing to prove, because otherwise we're just, no, I'm not going to convince anybody this is a good thing, worthwhile for us to do. Equality is reflexive, right? Reffle? Da-da-da. I'm done. All right. First level down. Let's prove something more interesting. If X and Y are natural numbers and Y equals X plus 7, then 2Y should equal 2 times X plus 7. Now, there's a few different ways you can prove this. What the natural number game, and you kind of work backwards a lot. I always think about taking my assumptions and moving forward into my goal. But the Lean way of proving often is actually just taking your goal and finding necessary conditions, moving back. Well, this goal is true if this is true. Then I'll prove that's true if this is true. Then I'll prove that's true. And eventually I'll move all the way back up into my assumption. Or it'll be the situation where if I have exact equality, y is equal to 7x plus 7, I should be able to substitute that in there, right? So the rewrite tactic is what lets me take the equality y equals x plus 7. If I rewrite, then the y gets replaced with x plus 7 because equality is literally the same thing. And now what can I do? What property of equality do I want to use? Flexivity. There we go. And then we have, okay, now we need to prove something really hard. 2 is the number after 0. Okay, so 2 is the successor of the successor of 0. Well, what is the definition of 2? 2 is the successor of 1. Well, what's 1? 1 is the successor of 0. So hopefully somewhere I have in here a theorem that I'm allowed to use that 1 is the successor of 0. Again, 1 is equal to the successor of 0. Great. I'm going to rewrite using that equivalence. 1 equals the successor of 0. It's going to be wrong because it's sec. Okay. That did not work because it did not have 1 in the target expression. This is what it's trying to do. It's trying to look for 1 in the expression and replace it with the successor of 0. I want to do the opposite of that. So I'll do a left arrow there. Great. So I'll turn my successor of 0 into 1. And then I believe I have at my disposal 2 is equal to the successor of 1. This is exactly 2 is equal to successor. But I'm using something advanced. Sorry. Let's just do a rewrite. Rewrite 2 equals successor. And now reflexivity. So I'm not going to prove to you all the different properties of natural numbers, because this is just a fun game. This is the place I would recommend that you start if you want to learn about this formalized stuff, because it's all math that you learn pretty early on in your career. So you don't have to worry about the math. You're just worrying about how do I get a handle on the code, right? This is probably a good point for me to pause and ask if there's any questions about what I'm talking about so far.
So you're using this to check the proof that you have in your mind. Is there like an output where it's stored that it was proved?
Right. So let's see how this looks in. So this is like the game. So right now it's the confetti emoji is the proof that it's been proven. Right. So level completed, the emoji, that only happens when all of my goals. So my original active goal was 2 equals the successor of 6 is equal to the successor of the successor of 0. I first proved that it's sufficient to prove that 2 is the successor of 1. Then, by this fact, that's going to be true as long as the successor of 1 is equal to the successor of 1. Well, that's true because of reflexivity, and therefore I'm done. So it's kind of this like backwards sort of argument that your goal, this is true because this is true, that's true because that's true, and that's true because of reflexivity. And so there's an artifact of it that is stored. It'll probably be easier if I just show you what actually the mathlib library looks like. So let me go ahead and so that, again, this is where I would suggest to start playing with this stuff. And then what if you want to actually contribute to the field of formalized mathematics, particularly if you're interested in the lean, And I forgot I said earlier, lean is not the oldest, but it's certainly the most active. It's where folks like Kevin Buzzard and Terrence Towle are putting in their work. It's just got the biggest active community that I'm familiar with in terms of contemporary mathematics and efforts to formalize mathematics. And so if you want to search for Lean Mathlib, it'll send you here to give you a trailhead. And again, it used to be like 3 years ago, if you wanted to do Lean, then what did you have to do? You had to learn to install the Lean programming language on your computer. Then you had to download, the right text editor, the right plugins for that text editor. So Emacs or Vim, if you have an opinion about that, or VS Code. It was a whole afternoon workshop to get you set up to use this stuff. I don't like workshops. I like big green buttons. And so that's where there's a big green button that these days you can press. It's not a big green button right now because I've already pressed it, but before I pressed it, there was a big green button right here that says create a code space. And I pre-baked the cake a little bit just to make this go a little bit faster for us. first. But here I have in my web browser, I have to be logged into GitHub, but you can do all this with a free GitHub account. I have here, there's a command line. If I need to, run command line things I can. I don't have to though. If you don't know what a command line is, don't worry about it. What I want to show you today is a little bit of topology that I've formalized in Lean. So this is actually a fact, a topological fact. I'll explain it. I'll try to do my best for those who have no topology background to follow along with what I'm talking about here. But this is a undergraduate, graduate, depending on what school you're at. Fact from topology. Let me find it here. And separated. There it is. So this lemma is one of several that I contributed to the MathLib over my sabbatical, because MathLib did not know that regular Lindelof topological spaces are normal spaces. What the heck do those words mean? Well, thank God we have a pi base, because I can just, if I don't know what any topology word means, I can just look it up here. Regular means a closed set and a point not contained are separated by open neighborhoods. Lindelof means every open cover has a countable subcover. This is what humans think of when they talk about Lindelof and regular, if they know a little bit of topology. So what I proved was as a lemma, because this is just the way that you do it naturally when you're proving, here, I'll actually just draw a picture for you here. Tuck this away here. So the idea of the proof is you want to prove that if you have a closed set S and a closed set T, there exists a certain type of cover called a separating cover. What that kind of cover is, it's a countable cover. N less than omega, that just means n is a natural number. And the idea is that these UNs cover the S. With the added property that their closures miss T. And the idea behind this is that if you could do this with a countable cover, then if you could do it both ways, you could do it backwards with the T against the S as well, then you actually can produce two open sets that don't intersect, and that's the classic definition of a normal topological space. All right, so this is the kind of thing that I want to prove. And it works because of regularity. The idea of the proof is how I actually get this is that the definition of regular is that every point has the neighborhood. That works. That's just the definition of, or a characterization of regular topological spaces. For every point in every closed set, there's an open set whose closure misses the closed set. I can do that for every point, but it may not be a countable collection. So it might be uncountably many points in S. So the natural thing to do is take advantage of the fact that I'm Lindelof. Again, Lindelof is that property that says that every open cover has a countable subcover. And therefore, we can take this collection right here, and we can find a countable subcollection, right? So we just do it for every point. Every point has an open set that misses T. And then that's for UX for every X and S. That's what I've got. And then by Lindelof, I can choose the U prime of UNs, a countable subcollection. It would still cover the set S. The closure of each individual open set will miss T. And that's not enough to get the normality property, but as a whole separate lemma, a whole separate theorem will actually use this. If you have it both ways, then you have the separated open sets around S and T. So that's all I'm going to try and do today. This is basically just applying the Lindelof property to take this cover of nice sets and get back the countable cover of nice sets that I needed. We kind of talk about what are the considerations that you have to go through, even though mathematically it's not terribly advanced, but how does one actually formally convince a computer of this? Any thoughts or questions before I show some code? Yeah.
This is how you do it. That is, you came up with this proof before, or you learned it from somebody else in a book?
Oh, classic argument from a book. Yeah. So.
From some mathematician, let's say.
Okay. Yeah.
And
So
this is not encoded already in the lean. That's what you did.
it wasn't before last summer. Yeah, or last spring. Is I took this classic argument. And in fact, it's used two different places. This separating cover, this countable cover of nice open sets whose closures miss other things. It's used in the proof that regular Lindelof spaces are normal. It's also used in the proof that perfectly normal spaces are completely normal, whatever those words mean, right? So it's one of those things where it happened twice. And in mathematics, just like computing, we don't like to repeat ourselves. So we want to have this lemma that said that if I can just find these separating covers, then I get the right kind of thing that I need every time. Okay,
One more question.
what's up?
I'm not familiar with topology. Is a cover just a collection of sets that like,
The union contains it.
okay, thank you.
Yep. Yeah, so specifically here we want an open cover, so every set should be an open set. It belongs to the topology. If you don't know much topology, just imagine circle disks without a boundary, all right, or any region without a boundary. R2 would work for the intuition here. All right, let me go ahead and get that tucked away, and I'm going to look at the code now. And so I've already proven this here. I need to zoom out actually a little bit if I want to fit it all on the screen. And this is where I already proved it. I'm going to prove the same lemma. I just called it has separating cover 2 instead of the regular has separating cover. And I went ahead and expanded. What is a separating cover? It is there exists a u. There exists a function u from the naturals to the subsets of x. S is contained in the union of the UNs. All right, so that's what it means to be a cover, basically. Here is a cover of sets that covers S. S is contained in the union of the UNs. And, well, this needs to be an open cover, which means that for every natural number, the UN that is spit out by this function is an open set. And I need to have that disjointness. The closure of each open set is disjoint from the other closed set T. So we're covering S with open sets whose closures miss T. That's essentially what we need to do this. And it needs to be a countable cover. Okay. Now, first of all, our very favorite friend in formalized mathematics, I think there's almost always called sorry. And I need to zoom in. I know it's kind of hard to, it's got to be all read it. So I'll just have to scroll back and forth, I guess, a little bit here. But sorry is basically where I don't know the proof. I know this is true. I've done enough mathematics. I know it's true, but I don't have a formal proof of it yet. So any time I don't know how to prove something, I'm just going to tell the theorem prover, sorry, I'll get to this later. And that way it doesn't throw an error, but it gives me a warning that you proved this, but you said sorry. So you didn't really prove it, right? You waved your hands at some point and said, sorry, no, that's true. Believe me, trust me. I'm going to try to remove sorries for us today. I don't know if I'll get that done in 15 minutes, but we're going to give it a shot. So in order to tackle this, the first thing I want to do is the thing that we almost always forget to do when we're doing human mathematics. There's some trivial case, right? We have X as a topological space. We've got S and T are subsets of X. I've got all this stuff. I've got all this machinery. Almost all this machinery assumes things are non-empty. So this is where I'm going to steal this line up from up here. There we go. Our cases is empty or non-empty X with empty X, non-empty X. What that does is it takes my goal, which is to prove that this open cover exists, and splits it into two subgoals, which I don't know how to prove yet, so I'm going to say sorry for both of them. But the first goal is the same, but I have this extra assumption that X is empty. The second goal is the same, but now I have the assumption that X is non-empty here. Okay, so let's do the empty case because that's almost always the easy one. And I think I can at least get that done for us today. If X is empty, is the empty topological space a topological space? Well, Lean has decided that yes, it is. Groups might have to have identity, fields might have to have, identity for addition multiplication, but topological spaces don't have to have points. Okay, that's fine. But hopefully we can get away with something pretty trivial, simple here. I need to find so now that everything's empty, what are my open sets gonna be? Everything's gonna be empty, right? Pretty much every object in this proof is gonna be an empty set. Let's see if I did this like an hour ago. Let's see if I can remember how to do this kind of slick. Well, I need to first give it my function, my u that takes natural numbers and spits out the right set. Okay, well maybe I can use the function that sends anything to the empty set. And sorry for the moment, because I haven't proven it yet. But we can see now that my goal has changed. It used to ask me, does there exist something? Now it says, because I'm using something, it says, all right, now prove everything else about the thing that you're using. Okay? All of my u's have turned into functions that send points to the empty set. Okay. So I actually have a few things to prove here. I've got this big conjunction right here. I've got this big and statement that my cursor's hovering over. So let's go ahead and split that up using the constructor into two sub-goals. And once lean catches up, there it goes. I can now see that my first sub-goal is just to show that S is a subset of the union of empty sets. Okay. Well, what can I do about that? Well, if X is empty, what do I know about S? S is a subset of X. X is empty. So S is the empty set, probably. Okay. And this is what's fun about lean, especially because I'm still somewhat a newbie here, is that how do I prove something so easy? Well, here's what I typically do. I just know that I have the fact that S is the empty set. All right, I know that's true. I decided that I'm going to make that my new goal by saying it is true, I'm making this claim that S is the empty set. And here's where I said that AI isn't always all that bad, because I could just say exact, cross my fingers. Oh, good, this is just a built-in fact that MathLib knows about. So now I have this theorem that S is equal to the empty set that I can rewrite with this. That rewrite thing from earlier that takes things and replaces them. Now, the empty set is a subset of the union of empty sets. That's obviously true, right? I hope so. Let's see. Yeah. And that's built into Lean as well. There it goes. This seems like a lot of like gobbledygook to prove something so very simple. And it is. When I actually proved it and the actual thing that got accepted, it was a one-liner. But, there's a bit of, magic in that you've got to learn to kind of get the slick, formalized versions of. But this is kind of the way we would think about it as a human, I think, down here. All right. The next bit here. I need to prove that for every natural number, so let me introduce my natural number. And actually, I don't care what it is. So I'll just call it the underscore, because remember, my function doesn't actually use the natural numbers. It always spits out the empty set. So no matter what I plug into the function, I don't care what that is, but I have to introduce it anyway. Now I've got to prove two things, a conjunction. So I'll use the constructor. And now I need to prove that the empty set is open. Again, that's kind of one of those axioms of topology, right? That better just be true. And sure enough, is open to empty is a built-in to the MathLib library. I don't have to reprove that simple fact. All right. Here's one that takes a little bit more work. I'm pretty sure if I write exact question mark here, it's going to choke. So we actually do something somewhat interesting mathematically at this stage. And so if it doesn't work immediately, that's probably not going to work. Oh gosh, really? I think it failed the other day. It just took a while to find it. What did I use? Disjoint of sub-singleton? That's a little bit magical. Wow, I didn't think that was going to have a one-liner. All right, let's go ahead and pretend it didn't have a one-liner. More interesting that way. Disjoint closure of empty and T. What's the closure of the empty set? Empty set. And here I actually had some issue when I was practicing this earlier. I had that the closure of the empty set is the empty set. And I try to sorry that out, and then it's gonna, I think it chokes here because. Give me a moment here, put another sorry. Yeah, now it's gonna yell at me. Because Lean is pretty good about guessing things sometimes, but sometimes it's like closure of the empty set in what topological space, Dr. Clements? Oh, I don't know, the one that we care about right here. So what I ended up doing in this situation is use a different tool called the Moogle. It's like Google, but for Lean. And I'm pretty sure that somewhere in Lean, there's a built-in the closure of the empty is empty. And if I mistype empty, maybe it's going to give it to me. Yeah, theorem closure empty. I'm going to rewrite closure empty. Oh, right, I can't do that. That's what I'm trying to prove here. So I can just get rid of that have statement and just rewrite the closure empty. So now I've taken my disjoint closure empty T. Now I want the disjoint of empty T. Now, of course, everything should be disjoint from an empty set, right? So maybe now I can do exact, of course, it worked a moment ago anyway, but now I get this kind of fun esoteric thing. What the hell does that even mean? I don't even know. But if you don't like that, then you can just go ahead and say, I'm pretty sure closure is symmetric. Not closure, excuse me, disjoint is symmetric. I can apply disjoint sim. So apply says, I have a theorem. And now I don't have empty T, I have empty empty, and I believe that actually belongs to the mathlib as disjoint empty. It is a fact disjoint of any set with the empty set. That is a fact. It's exactly disjoint empty. It's yelling at me because it's underscore empty and lowercase disjoint. Oh, but it's not S, it's T, right? So I gotta leave that at T. Yeah. All right. So again, this is kind of like the way you get started doing this sort of thing. It gets to be a lot more closer to what you'd actually do. Again, these one-liners right here. Actually, I think 2 lines right here do everything that I just did down below. But being able to chain these things together and almost get to the point where, well, this is just true, obviously, right? This is what we would say if we're writing it up. But to formalize it with the computer, there's a bit of practice in my experience of working with these AI tools to help fill in, to complete your sentences, basically, right? You know what's true. You know that someone else has certainly proven this and contributed this to MathLib before. And so you can use these tools between the Moogle and the apply question mark and the exact question mark to dig up these existing proofs that are known, right, to the MathLib. You use that to kind of fill in your gaps. And then taking all this and turning it into 2 lines, that's just a matter of learning how to chain things together. Things like constructor I could have done is open empty, and then I think it's, yeah. And then I could have gotten rid of 1 line right here, by just doing this live, so I may have messed that up somehow. Why was it yelling at me? So just get rid of that. Yeah, did prepare that bit. So there's a way to take this very simple. The fact that the one part of the proof is just the is open empty, just feed it directly into, oh, I got it. Exact is open empty. Now I can get rid of that. Almost got there. But yeah, doing that I'm going off script. That's always a mistake. Never live code. It's always a mistake. So that's kind of the game right there. Yeah, yes, Jamie.
So what I'm taking away from this is that your hope is that enough mathematicians will contribute to the, actually rewind, can I ask the question first? When you are doing this coding, is this contributing to some database that other people can then use from you where you have done proof in this computer code, where they can then use your proofs later.
Yes, exactly right. That's what the math lib is.
Okay, and so
Yes, sir.
the hope is that enough mathematicians will code the low-level things and then build slowly but surely, so that sooner or later, students can do proofs with building blocks.
Well, that and also so that we could do hard research mathematics with having all the tools. So all the things that we just say are obviously because we've taken our graduate courses and we just know all this math. But not a lot of it's been formalized, right? This
But
is
it's
a community effort to build up the corpus of mathematical knowledge into a formalized library. That's what the math lib is. So this is on GitHub, like a lot of open source software is. It's on GitHub. And so if you go to the math lib Git repository, you can go to math lib, you can go to the math lib folder, you can search for your favorite field of mathematics. And again, I'm a topologist, so I've contributed to the topology library. And then here is this separation library of all these different results about T0 spaces, T1 spaces, T2 spaces, regular, normal, all these things that make sense to me because I'm a topologist, but don't expect everyone else to know about. But at some point, there was no proof in MathLib that regular Lindelof spaces are normal. And that was kind of one of the big things that I contributed was to add that. It's again, super well-known result for researchers, which is why we're still kind of in the early stages in some fields, at least in certain fields of mathematics. Yes.
There are many, many terms that are used in many, many ways in mathematics, non-unique terms. How does it guard against that?
Yeah, namespacing is a huge thing. I kind of used it silently here. It's like FinMap. I'm not sure what FinMap actually is, but it has its own disjoint empty theorem. Set has its own disjoint empty theorem. So we have this kind of namespacing with this dot notation, where if you have the same name for two different things, you might have it
like normal.
Yeah, like normal, exactly right, yeah. So a normal, good point. So what is normal called here? It's called normal space. I think that was the trick here. It's normal. We don't just call it normal in MathLib. It's normal space is the name of the property, which does a little bit better job. At least it distinguishes it from a normal subgroup, for instance, right? But yeah, so there's a lot of that business. And there's the fact that my personal belief is MathLib will only get so far before it just can't do everything. There's going to be at some point where MathLib is going to be kind of like the core of mathematical knowledge that's formalized. And then people will have their own libraries that they write that depend on the MathLib for their own particular. And then you have to worry about namespace collisions with somebody else in a different field of mathematics. You're both using the known facts from MathLib, but then your stuff can conflict with their stuff in terms of names, not in terms of accuracy. You won't have to worry about coordinating because right now we've got hundreds of contributors to this. They're trying to build this one cohesive mathematics package. That's a hard job. One of the things that I said I would do over the summer and never got around to is the fact that there was, just for historical reasons, this notion of separated neighborhoods. For every two sets, there are open sets that are disjoint that contain them. These days, the more conventional way is to use disjoint. If I can find it, the way it's used correctly. I may not find it fast enough here. Yeah, so disjoint, this is another issue of where things are overloaded. This disjoint does not mean that the neighborhoods of X and the peers of Y don't intersect. It means that every member of this doesn't intersect every member of that. It's like a filter notion of disjointedness. And so we get this overloading of concepts here. But at the end of the day, if you sets being disjoint, you could characterize that as a filter. That's a lot of what also happens in the Pi base. Like a lot of topology, is actually described in terms of, like we don't describe it in terms of open sets so much as the neighborhood filter on the space. And because it's just, you have so much facts about filters that you get things for free.
Is there any concern that an argument here might wind up wandering into different categories? And coming back with
That's a lot of what happens so again, this is a community effort. So if you go to the MathLib Zulib, there's a whole online chat that I don't know if I can pull it up quickly here. Yeah, here's a read-only version of it. Yeah. So there's lots of conversation. A lot of the conversations with people, like I can make correct mathematics in the MathLib, that does not mean it's going to get pulled in. Because I might prove something very esoteric that I'm interested in, and that'll be one reason we get rejected. Or I'll prove something specifically in topology, but really it's an order theoretic fact. I can prove it about filters and I get the topology as a corollary for free. And so a lot of that, just like, you can submit a correct paper to your favorite journal. They might send it back and go, this is correct, but it's interesting or not well motivated, or it's the same sort of peer review sort of process, except it doesn't count for, standard promotion considerations, at least not today. But yeah, that's a lot of it and that's the community effort, is to try to find the most sensible way that serves the most amount of mathematicians to create this corpus of formalized mathematical knowledge.
Steve, with this tool, presumably as it gets built up and used for more serious purposes, research.
Again, people are getting 1 million. I lost the tab. We haven't someone trying to prove Fermat's theorem and getting £1 million to do it, right? So it's certain areas it's way more advanced. I think in general topology, my little niche of mathematics, it's not nearly as prolific because a lot of people are drawn to my field, I think, because they don't like computers. I don't know why. It's kind of math that it's just on paper. But I interrupted you. I'm sorry.
Oh, no problem. But presumably more and more axioms will have to be added, right? Just as, it gets more.
What do you mean by more and more axioms?
Well, and I'm speaking as somebody, I'm not sure if I'm a mathematician per se.
Right.
But presumably, there's no limit to the number of axioms we have to add if we want to continue to prove things.
Mm-hmm.
So is it easy to see, actually go in and see what axioms are these results relying on?
Yeah, so it's kind of funny because I'm, being a set theoretic topologist, I know a lot about, the ZFC model of set theory. I'm actually not that clued into the foundations of MathLib. I know it uses a certain type of type theory instead of set theory as its basis, but I'm actually kind of a naive in terms of mathematician user of it. Trying to see if I can find it quickly enough, and I'm not going to. But there is a whole other people have thought about this. And of course, Gödel's incompleteness theorem says at the end of the day, if you can prove that this thing is consistent, then it's not consistent. So it's just like we can't have really strong promises about that. But there's already a well thought up foundation for how Oh, and there's other kind of neat things so one thing that differentiates lean, I think why it got popular with mathematicians and not the other things that came before it. A lot of the other proof of systems that came before it were really interesting to computer scientists and constructive mathematics. But in lean, we have a law of excluded middle. And I used that a moment ago, right? Everything's empty or not empty. I took advantage of that fact to prove something. And some people are offended by that, at least on the constructive mathematics or computer science side. But we do have law of excluded middle and a lot of the other, we have choice. You have to, so the axiom of choice, if you're not familiar, is that lock socks thing. If I have, infinitely many pairs of socks, I can say I can pick a random sock from each pair. That is something that you can use in a proof in lean. You do have to kind of say, hey, this is a classical proof, not a constructive proof when you do that. But there are people thinking about these sorts of alternative foundations and trying to, at the end of the day, what I like about lean is that it's being built by mathematicians to help do better mathematics rather than computer scientists who are just interested in building theorem provers as a computer science exercise. Yeah.
I have a few questions. So 20 years from now, when you're doing model that you're foreseeing, what's the purpose of it? What's the purpose of math? How used is it going to be, or how embedded is it going to be in all the processes that you started in the beginning of your talk?
We're going to be able to prove things that are too complicated, or we're going to have formalized proofs of things that are too complicated for any human to ever grok, to ever understand. It's just going to allow us to prove things that we can't prove before, one. Two, it's going to give us tools, especially someone who thinks a lot about education. Oh, there's something I should show off. This is not lean, but it's called Lurch. The Lurch project. And I love this tool. I learned about this. Wish they had a good, where's the tutorial? This is a much nicer version of lean, which looks like Google Docs, but it actually does, if it's going to load for us today. It actually, can I pull in an example? Just kidding. Anyway, this is an example of trying to take formalized backends but then using it to verify students' proofs, right? So students, as they're typing something in kind of like a natural language, it actually formalizes it for them, verifies it, gives them feedback, and immediately lets them know if their proof is valid or not.
What about verifying the correctness of what's now an academic article that I'm submitting to a journal? Would you be favorable to having these kind of programs check the correctness of a submitted paper?
Well, I'm thinking like in 20 years, there are a million journals that will require you to have a formalized
Okay, so
backing because the proof math we're going to be doing in 20 years is just so complicated that a human reviewer can't.
Okay, so then second question, aren't you worried that in 20 years people are going to be discouraged from doing groundbreaking in mathematics because quite frankly it's not been written in Lean or is not really embedded in MATLAB. So for instance, I'm too old, but Tariq might discover that he's Grothendieck overnight and he's going to define the notion of cloaking, which is the whole field of mathematics, far more generalizing the categorization. But Tariq is never going to write his paper and not invent a new branch of mathematics because it's not written in Lean and it's really hard to do it.
Yeah,
So
yeah, I'm
what do you do
absolutely
with
worried. I'm terrified. I mean, here's the thing, right? I didn't talk a lot about generative AI, but like, we are not that many years away from stick your chat GPT, have it spit out the bullshit, which is the academic term for it, into Lean language. Now, when Matt with chat GPT spits out a proof in LaTeX, it's not checked, right? And so the student takes it and gives it to you. Now, spit out in Lean, get it verified, give the generative AI model feedback, learn from that, hand it back. That's something I meant to grab. There's actually a research paper on this. They're actually starting to find a way to wire generative AI with formalized tools like Lean. We're going to have master's theses pumped out, by AI in like the next 5 years. Like, you just ask a question that you would ask your grad student to spend 2 years on, and they could have a full 20-page paper on it produced automatically. That's wild. And I don't know. I don't have the good answer for what that's going to mean for us. This is why we need to be thinking about it, though.
Well, this is a good segue in the third question, and this is where words like terrifying come. When you're doing your demonstration there, right? At some point, you were constantly checking against what Lean thinks about it, right?
Yeah.
So if this becomes so popular, I'm worried about this thing. I'm going to learn not to do proofs by the way I was taught by actual human geniuses, but I'm going to learn to do Lean type proofs, right? So I'm worried about the education process because I'm hoping that even in 20 years, 200 years, where the machines are going to do everything for us, there's still going to be some human overlords checking it, right? Who's going to teach the human overlords to think human, not Lean-like, right?
Well, this is where I think a lot of like the literature is going to be more expository in nature, right? You could have these proofs. Yeah.
I'm afraid that, it's in human nature. If I have such a good tool and it gets better and better, and it tells me like, look, this is a quicker argument, what's my incentive to actually bang my head against the wall, spend 2 days and come with a arguably longer argument that spans other ideas, right? See what I'm saying?
Well, we have symbolic integration tools. We've had those calculators for years. We still teach calculus.
Yeah, but are you proving any clear new theorems in calculus?
No.
No, because we're self-sufficient with what we have, and we let it build the enough computer.
But we're still computing the same things we did in calculus. So I think it's just another tool. It's another tool that we need to be aware of because Pandora's box is open. And it's not going to be me that makes it, breaks what's going to happen with this future. But it's a tool that we can use it for good. It's a tool that we need to be aware of because it's going to just change the game, whether we like it or not. So, yes.
Just to add to that argument, I know Kevin's motivation was more to verify the existing papers because it's, as you pointed out at the beginning, I had a long conversation with Kevin on this topic actually. So the idea was, as there might be many papers with some errors that are cited by other papers, there might be a whole chain of papers with incorrect.
Maybe we pull out that domino and the whole thing. How do we know?
So the motivation was really to, verify.
Yeah, that's the thing. This tool, I can see this tool checking proofs or something, but creating their own proofs, I don't know how that's going to do it. Math requires ingenuity. we're gonna have. I mean, I'm pretty sure if I could be in computer science, I could teach my computer how to, do Van Gogh paintings, and I could probably produce like 100 Van Gogh type paintings. Right, but I mean, we don't want to be stuck just having Van Goghs hanging in our rooms, right? So I mean the creativity of it, I don't know how that. I mean, you have all these tools in the library, but how will it actually? So you're saying it will come up with their own proofs?
I mean, at a certain point, logic bot's gonna prove everything for us, right? So this is just purely running through symbolic logic, every single like permutation of symbols, verify if it's true or false. Give it enough time, million monkeys in the typewriters, right?
Yeah, it can check things, right?
It can check things.
Okay, so you're saying basically like it could potentially write all possible proofs and then find the correct one. Is that? It would take a long time, I think.
There's a combinatorial explosion here, thankfully, that'll protect us a bit. As computing power gets more involved, and the fact is that it's not going to. We're able to step back a bit here. We're not just proving, symbolic calculus, right? We have all these theorems and tools within the math lab and these other formalized libraries that we have bigger puzzle pieces that we can try to fit together. In the computer, you already saw me doing that basically today. I used exact question mark, and all that did was use a single theorem. There's something that I'm not used to using it called ASOP, which is actually able to chain together 3 or 4 different theorems to try to attack the goal that you're trying to prove. So it'll just tell you the 4 lines that you need, and those tools are only going to get better.
Yeah, I mean, what I can see, I could see like giving a computer all of Klotz's papers and then let the computer decide whether Klotz's methods are good enough to prove this result or something. But what result I want to prove in the future, what's an interesting result, I'm not sure the computers will be able to do that.
Well, computers won't be able to decide what's interesting. I know we're out of time, so this will be the last question. Computers can't decide what's interesting, but once you decide something's interesting and you can formally ask the question, these tools are going to be able to take a crack at answering it automatically. If it's a trivial question, then they can answer it. If it's less trivial, then it's just a matter of the computing power. But until then, there's going to be some human ability to interject and to.
Is it going to give you the argument?
What's that?
I'm still not sure. Is it going to give you the argument or is it just going to say yes?
It's going to give you the argument. It can't say yes. So in MATLAB, in formalized mathematics, you can't just say things are true or false. You can only have proofs. You can only construct proofs. And so it will only say yes if it has a witness to the truth of that statement.
The proof will be intelligible.
Well, I mean, define intelligible. It might be 1,000 lines of code, right? So, yeah. So at that point, it depends on your opinion. But we are definitely on. I'll hang out and chat with folks who want to, but thanks so much for your time today. Hopefully that was